Welcome to week 3 of the deep learning course. This week we're going to talk about recurrent neural networks. Recurrent neural networks are networks for sequences, so that can be time sequences or biological sequences and so on. So the plan for today is first to talk about what we can use recurrent neural networks for. Part 2, how are they trained. Part 3, I will give an example from some research in my own research group where I will focus on the attention mechanism that we use to help improve the performance of the system, because it doesn't have to integrate information over the whole sequence. It can kind of zoom in to relevant parts of the sequence. And then in the part 4, I will talk about what we have learned so far in the course on supervised learning. Yes, so part 1, recurrent neural networks. And here's kind of where we are in the roadmap. So we have reached the third model, the recurrent neural network. So a good way to motivate recurrent neural networks is to talk about a very successful application of deep recurrent neural networks. And of course, if you think about sequences, speech, I'm speaking right now, this is what we can use also recurrent neural networks for, to recognize speech, to recognize and transcribe what is being said. Here I have cut out the title page of the deep speech paper, which is a paper done by Baidu's Baidu Research Silicon Valley Lab, led by Andrew Ng, a very famous researcher in the field. And I also taken a figure from the paper that kind of shows the setup of the model. And you can see it looks a little bit kind of like the model we have seen so far in the course. The important new addition here are the red and the blue and the red arrows that indicate connections in the neural network over time. This system, I'll go more into detail with it in the coming slides. But this system exists in 2 versions. So they also the same group released a Deep Speech 2 paper where they say that they have reached human level performance in speech recognition, and they are also built with the help of GPU programming a real-time server. So that means that if you speak to your smartphone, this will be sent to their server, and in real time you can get transcribed speech back. Yes, okay, so let's try to understand the recurrent architecture. So the only addition we make compared to the standard feed-forward neural network is that we have connections over time. So this is drawn here in this figure that looks like a hairball. We'll use in the coming slides, we'll use a different notation where we unroll the network and it becomes much more clear what we are doing. And we'll also see the connection to deep learning, where kind of we make the models in the recurrent setting, we make some models deep along the temporal axis instead of like in the other axis. Of course, we can make it deep in both directions, but you can think about recurrent neural network as a model like a feed-forward model, which is as deep as the number of time steps. Okay, so in equations we have here for the activation of the first hidden layer consists of a contribution coming from the inputs. So this is this W superscript 1, as we know from the feed-forward notation. And then we also have an additional term where I have used this arrow to indicate that this is a connection that runs over time. So you can see that you get the contribution from the input to the network at time t, and then you also get a delayed contribution from the hidden state from the previous time step. Right, so there's a memory effect going on here. So information about what has been presented to the network is summarized in the hidden state from the previous step. And this, of course, this previous step has already in the same fashion accumulated information further from the past. So that means that in this way we in principle can accumulate information back in time as long as we need it. And then the H2, H superscript 2 at time t is simply just the normal feed forward connection here. Yes, and if we do, as I said, we can unroll, we can draw the same network with the same equations in a different way, where we have each column here is one feed forward neural network, and then the forward connection in time is called W2. In the drawing is what I call W superscript arrow. So it actually means, W2 here is what I call W arrow. And you can see now that if you draw it in this way, the unrolled way, where you have one column for each time step, then you have a lot of weight sharing, because the weights from going upwards, that's the same in each time step for each column, and in the same way the arrows forward in time are the same for the weights for the time propagated signal. And you can also importantly here is that you should think about this as kind of a network that is updated in discrete time steps. So all horizontal arrows, they are instantaneous, so they send the signal immediately from one at the same time step upwards, but the lateral connections, they are delayed one time step. So that's how the signal is propagated through this network. Yeah, so let's go back to the deep speech architecture and let's try to understand it a little bit better. So first of all, the way that we represent speech here is by a spectrogram. So that means that we make time windows, and then we take the Fourier transform of the speech, and then we get this kind of a movie of the kind of, on the y-axis is the frequency, the energy frequency content for different frequency bands, and on the x-axis is the time going on. And the network now is a convolutional neural network in the first layer, so that means that it integrates, it has filters that kind of attend a certain time period, and that is sent up to as an input to the network at time t.